Hello everyone and welcome back to the good stuff we have been doing. So today in this video we have a very interesting problem before us to solve, and that is the integral from 0 to infinity of cosine of ax divided by x squared plus b squared dx. Now this is a very interesting problem for quite a number of reasons, and we have offered a very good solution to this problem before on this page, and that one involved the use of the Cauchy-Chomley transformation, where we began with expressing cosine of ax as an infinite series in Taylor series, which is the sum as n runs from 0 to infinity of negative 1 to the n x to the 2n divided by 2n factorial and so forth. And we substituted the series here and swapped the order of integration, and it was a very lovely solution. Please do check the description. You will find it in the link below. But for this problem now, we're not going to use, for this case, we're not going to use this method. We're going to use the fact that we're going to use Laplace transform, and we're going to explore the fact that the inverse Laplace transform of the Laplace transform of f of x is actually equal to f of x. So it's more like if you take the Laplace transform of f of x and you take its inverse transform, you extract the function f of x. So for that, this whole expression will say this is the inverse Laplace transform of what? Of the Laplace transform of f of x, and the f of x is this integral of the integral from 0 to infinity of cosine of ax all divided by x squared plus b squared then dx. And then you would next up, what we'll do here is that we would observe that the Laplace transform of f of x actually equals the integral from 0 to infinity of e to the negative sa of f of x dA. Yes. Or rather, I should write f of e. What I should write x here, x here, and then x here. Then you have dx, of course. So in this case, you will have the inverse Laplace transform of what? You would have the integral from 0 to infinity of e to the negative s. Then this would be in terms of e. So we have an e, and then you would have the integral from 0 to infinity of what? Cosine of ax all divided by x squared plus bx dx, and then you would have the a. And now we have a double integral, and that is a good thing to worry about. Although it may look complicated, but this is actually a way forward. It's more like we have to sometimes complicate matters in order to simplify matters. So from here henceforth, this is the inverse Laplace transform of what? Now here in this case here, you would have to put this as integral from 0 to infinity of the integral from 0 to infinity. Then you have a e to the negative sa cosine of ax all divided by x squared plus b squared. Then you have dx, and then you have dA. Now next up, what we're going to do is that we're going to notice that we can do with respect to a first before doing with respect to x. So in this case, you would obtain the inverse Laplace transform of what? The integral from 0 to infinity of 1 over x squared plus b squared. Then you have to evaluate the integral from 0 to infinity of e to the negative sa. Then you have cosine of ax. Then you have cosine of ax, then dA, and then you would have dx. So now this is a well-known standard Laplace transform. Of course, this is equal to s divided by s squared plus b squared. So this is s squared plus s squared rather. So this is going to equal the inverse Laplace transform of what? The integral from 0 to infinity of 1 over x squared plus b squared times what? S divided by s squared plus x squared. Then you have dx. Now good things are happening already. So from having a double integral, we now have a singular integral to worry about. So this is the inverse Laplace transform of, now we can put this in partial fraction. I think the best way is to assume you have something like 1 over x squared plus b squared minus 1 over x squared minus plus x squared. So in this case, you have an s squared plus s squared minus x squared minus b squared. So you get that this is going to be s squared minus b squared. So you will always have an s here, then you have an s squared minus b squared. So then you would have the integral from 0 to infinity. Okay, then on the first part you have a 1 over x squared plus b squared dx, and then minus integral from 0 to infinity of 1 over x squared plus x squared dx. So good things are happening already. Now the first integral is going to be pi over 2 because okay, no, this is going to be 1 over b. Let's write it. This is going to be inverse Laplace transform of what? S over s squared plus b, okay, not a plus sign but a minus, s squared minus b squared. Then you have a 1 over b times what? The tan inverse of what? I think x over b. And then you also have 1 over s times the tan inverse of x over s, and everything is going to run from 0 to infinity. Now if we evaluate this, each of them is pi over 2, pi over 2. So you could write this as the inverse Laplace transform of s divided by s squared minus b squared. Then you would have a pi over 2b minus pi over 2s. So there, I guess that's because this is pi over 2 times b. Okay, now you can factor the pi over 2 outside. So you have a pi over 2 times the inverse Laplace transform of s, all divided by s squared minus b squared times what? 1 over times s minus b divided by bs. So the s here cancel the s here, the s minus b cancel one of this s minus b. So you would have the inverse. Okay, we can even factor the b. So you have pi over 2b times the inverse Laplace transform of 1 over s plus b. Okay, now this is, it now remains to evaluate the inverse Laplace transform of 1 over s plus b. And of course this is going to equal pi over 2b times what? E to the negative ab. And this is the answer we got from our original expression, right? Yes, that's the answer we got. This is answer we got from our from like using our previous method. And that video was almost, I think it's, I don't know, maybe 30 minutes or 20 minutes or so. But this is I'm on 8 minutes of recording now, and we already found our answer. And okay, you might ask me, how can we prove this is a Laplace transform? Well, it's simple. Assume that, for example, now you want to take the Laplace transform, but there is integral from 0 to infinity of this expression. You have integral from negative sa times what? E to the negative ab, right? dA. So you would here have the integral from 0 to infinity. You have e to the negative, so you can factor out the a. So you have an s plus b a times dA. Of course, this will be 1 over s plus b. So that is how we got that expression here. So everything checks well now, and we have our solution with us. Thank you very much for watching, and please do subscribe to the channel. Bye and enjoy your day. Thank you.